So we are now discussing about how to find the transfer function of a rotational mechanical system. So a rotational mechanical system is given here. There are two moment of inertia, that is J1 and J2. In between J1 and J2, a spring and a damper B12 is connected. Another damper B that is connected to a lever. A torque T is applied here. With respect to this torque T that is applied, there will be an angular displacement theta 1 corresponding to J1, and because of the combined effect of this torque there will be an angular displacement theta 2 here. So now we have to get the transfer function of the given mechanical system. So in order to get the transfer function, first we have to draw the free body diagram with respect to J1 and with respect to J2. As in the case of mechanical translation system, we are considering similar to or analogous to mechanical translation system. In the mechanical translation system, mass, with respect to mass, we were drawing the free body diagram. Here we can draw the free body diagram with respect to moment of inertia, that is here with respect to J1 and with respect to J2. So with respect to J1, when you draw the free body diagram, J1, we are applying a torque here, and corresponding to that torque an angular displacement theta 1. So there will be opposing torques because of this applied input torque. So what are the opposing torques? Opposing torques will be with respect to T J1, that is torque due to moment of inertia J1, then torque due to spring K and torque due to damper B12. Now we can write the equation, that is applied input torque is equal to Tj1 plus Tk plus Tb12. Now if we write the differential equation governing this system, T is equal to, what is Tj1? Tj1 is the torque produced or opposing torque due to moment of inertia J1, and which is equal to J1 into d square theta 1 divided by dt square, plus what is Tk? Since K is connected between J1 and J2, Tk will be K into theta 1 minus theta 2. This is because we are considering the equation with respect to J1, and Tb2 will be plus B12 into d by dt of theta 1 minus theta 2. So this is the equation, differential equation with respect to J1. Now if we take the Laplace, we can write the equation as T is equal to J1 S square theta 1 of S plus K into theta 1 of S plus minus K into theta 2 of S plus B12S into theta 1 of S minus B12S into theta 2 of S. If we rewrite the equation, we can write this equation as T is equal to, taking theta 1 of S and theta 2 of S common, J1 S square plus K plus B12S into theta 1 of S minus K plus B12S into theta 2 of S. This is your equation number 1. This is your equation number 1. Now consider the free body diagram. Now consider the free body diagram with respect to J2. So for that, again draw a diagram J2. We know there is no direct torque applied here, but there will be opposing torques because of the combined effect, and there will be an angular displacement theta 2 with respect to J2. So the opposing torques are due to Tj2. Then the other elements connected. A damper B is connected to J2 and the lever, so TB, and spring TK and TB2 is connected between J12 and JB2. So we can write the equation as TJ2 plus TB plus TB12 plus TK equal to 0. Since there is no direct force, we can write the equation like this. Now what is Tj2? Tj2 is equal to J2 into d square theta 2 by dt square plus B into d theta 2 by dt plus B12 into d by dt of theta 2 minus theta 1, since we are considering the equation with respect to J2. The equation of TB12 is B12 into d by dt of theta 2 minus theta 1, and Tk is k into theta 2 minus theta 1. Now if you take the Laplace transform, so this is equal to what? This is equal to 0. Now if we take the Laplace transform and arrange the terms of theta 1 and theta 2 common, we can write the equation as J2 square J2 square plus Bs plus B12s plus k into theta 2 of s minus s into B12 plus k into theta 1 of s, which is equal to 0. So this is our equation number 2. So we got two equations. Now if we get an expression for theta 1 of s in terms of theta 2 of s, then from the equation number 2, we can write theta 1 of s is equal to J2 square plus Bs plus B12 s plus k into theta 2 of s divided by s B12 plus k. So this is the expression for theta 1 of s, and when you substitute this equation, that is equation number 3, in equation number 1, you will get an expression of we will get an equation with torque is equal to torque and in terms of theta 2 of s, and we can write the transfer function theta 2 of s by theta 1 of s, or else we can directly apply the Cramer's rule. So when you substitute this equation for theta 1 of s in equation 1, when you substitute the equation for theta 1 of s in equation 1, then we can write the transfer function theta 2 of s by t of s equal to, we will get an expression like this, s into b12 plus k divided by j1 s square plus sb12 plus k j2 s square plus sb12 plus sb plus k minus sb12 plus k all square. You will get an expression like this. This is the transfer function theta 2 of s by theta t of s. And if you want to write the transfer function theta 1 of s divided by t of s, then you have to write an expression for theta 2 of s. From equation number 2, you have to write an expression for theta 2 of s in terms of theta 1 of s and substitute it in equation 1. Then you can write the transfer function theta 1 of s divided by t of s. So, also you can do this problem by applying Cramer's rule. That means you only have to write the matrix equation and directly apply the Cramer's rule in order to find theta 1 of s and theta 2 of s. Then the numerator will be, then you will be easily able to write the transfer function. Now, for directly writing the matrix, in order to write the matrix directly, so we know what are the there are two moment of inertias, that are J1 and J2. Hence, our system or matrix will be of the order 2 by 2. So, first draw a matrix and this will be theta 1 of s and theta 2 of s, and the output it will be torque is applied to only first moment of inertia. So, T of s and corresponding to next moment of inertia, that is J2, there is no direct torque applied, so it is 0. Now, suppose this element is A11, this is A12, this is A21 and this is A22. So, consider the diagonal elements. What are the torques associated with J1? Tj1, Tk and B12. So, with respect to torque associated with J1, we can write the equation as J1 s square plus what are the other elements connected to the moment of inertia J1, that is K and B12. So, B12 s plus K, that is A11. Now, for off diagonal elements you have to give a negative sign. So, negative. Now, what are the elements that is connected in between J1 and J2 or associated with both J1 and J2? That is only K and B12. So, we can write it as S into B12 plus K. Similarly, A21 also you give a negative sign, that is off diagonal elements. So, A21 means the elements associated with node 2 and 1, that is J2 and J1. This again same as B12 and K. So, we can write the equation as S B12 plus Now the basic elements that are connected to J2. So the equation will be S square J2 plus there is a damper B that is only connected to J2 and a lever. So it will be SB plus the other elements are B12 and K. So K plus SB12. So by this method also you can directly write the matrix. So if you get this matrix, you can find the transfer function using Cramer's rule. So thank you.